All right, so here we are. We have done the deal. We've made the algorithm, we've validated it, we've turned the knobs and the dials on the algorithm back and forth and found the best version. Right? How do we know we found the best version? Oops, we forgot to talk about how to assess models. All right, so as we mentioned during a validation phase, we want to find the best model. How do we measure best? Well, there's a lot of different ways. There are dozens and dozens of metrics. Okay, each one is appropriate to a given task. So it really depends on what you're trying to accomplish. But here I'm going to throw out a list of very common metrics. Okay, very common ways that we might want to understand how good a machine learning algorithm is doing. So as you can see in this list, there are reasons to use them. So if you're after continuous data, like from a regression, then something like root mean squared error is going to be your cup of tea. All right. So the sum of squares error that I was talking about was summing up all those little lines, right? All those little errors. So that's the sum of squared errors. Well, root mean squared error is just if you take the sum of squares and you divide it by the number, you get to mean, and then you put a square root on it, baby. So, the details are not important, actually. What is important is that we are just using this as a measure of, how far off the regression was from perfect, right? Here's all our data points, right? Here's our line of regression, right? How much are these errors? That's what we're going to find out. Overall, how big are they? And we're going to say that this is a better fit than if if we had data points that were far out all the time, right? Huge outliers, then we would say that that line of regression is less well done, okay? So something like root mean squared error, which again is highly related to these errors that we're talking about, the horizontal distance away from the line, the vertical distance away from the line, right? Those are highly related, and that's all right, sorry, my bad. That's the kind of thing we're after here. So root mean squared error is one way to measure continuous variables like regressions. All right, the rest of this list is about categorical stuff when we classify things. So accuracy is like what percent were predicted correctly. Okay, accuracy is a simple, obvious, and easy metric. So how many of the sick people were sick? How many were well? All right. But one thing about accuracy is it doesn't get at which direction we make mistakes. It's only just that mistakes were made. This is what percentage of samples we made a mistake on. So sensitivity, specificity, precision, F1 score. Remember when we showed on the metrics thing? These are all ways to get at, how many false positives did we have? How many false negative? Okay? What percentage of those that were negative were predicted to be negative, right? What percent of those that were positive were predicted to be positive? Okay? So these are all appropriate in different circumstances when it depends on what we're trying to accomplish. All right. So, as you can tell, metrics is not something that we can give you an answer to. It's a very broad field, and what's appropriate is very much determined by what your task is, what the data look like, what you're trying to understand as good performance. So let's have a moment. I'm going to let you use all this newly gained knowledge to play some games here. All right? We're gonna have you do several slides of this, operating with all this newfound knowledge and seeing how good you are. All right? So, when you predict somebody's emotion from a facial image, how would you approach this in machine learning? What kind of a problem is it? So this is kind of output you want, right? After being trained on a bunch of these, it figures out whether you're surprised or happy, etc., etc. So what do you think? Would this be supervised, unsupervised? Is it classification or regression? Well, I'm going to tell you that this is the obvious answer, right? Supervised classification problem. There's a discrete number of emotions that we're after, and we can label them and tell the machine how to learn them. It is possible to do it this way. Okay, an unsupervised algorithm doing clustering, and we, after the fact, go after it. But that's not the kind of state of the art in a system like this. This is truly one of my favorite photos in the world. All right. So here's another one. You've been given a data set with a number of features, and you want to predict the individual's age. What are you going to do? Oh no, we've used this example, this exact example. I hope you remember. Okay, after predicting each person's age, how would you assess the model? All right, a regression. We're right in there. Now, the root mean squared error is the average, the square root of the average sum of squares, right? So when errors get bigger, they're worse. Okay, so we don't want these things. This is what we would like. All right, so hopefully your knowledge when you took the forms and did your quiz matches all that. Let's just finish off with a high-level overview. If you remember, what we did was we consulted our Oracle Google, the machine learning Oracle, and we asked it what itself is. What is Google? What are you, Google? Machine learning is just, and there's a lot of answers, and in one way or another, they're all kind of correct, right? That machine learning is highly statistical, that regression is a form of machine learning. We talked about the fact that machine learning is something where the machine adapts, right? It changes how good it is in response to the data that it's given. I'm going to give you a slightly different view in the end here, okay? So machine learning is just picking an appropriate model and then minimizing a loss function, okay? So the model itself is a combination of all these different things that we've been talking about. The machine learning model is the algorithm, it's the parameters set for it, and it's the features that we give it, the data that we give it to operate on. Okay, let's understand how it is that machine learning really is just picking a model and then minimizing a loss function. So as I said a second ago, the model is equal to both the algorithm being used, any dials we have to set on the algorithm about how it's going to operate, and the data features. Okay, so we want to pick a kind of machine learning algorithm based on the task, right? So if you're trying to do continuous number prediction, regression is the right kind of answer, right? And if you're trying to do classification, you have several things to choose from, including the decision tree, okay? And there are literally hundreds of other choices for these. But, so we're going to pick a simple-ish algorithm and we're going to try to solve it, okay? But that that algorithm could have hyperparameters to it. Ugh, why? Okay, it could have hyperparameters, settings that we dial back and forth, all right? Some of those algorithms have settings that we have to choose from a large number or potentially infinite number of choices because parameters are often real values, right? So there's an infinite number of things that you could choose for a given parameter. So how do we pick one of these? Well, we can use that validation process we talked about, right? We can use the validation process to pick among algorithms. We could try out, this kind of regression and that kind of regression and a third kind of regression, okay? We can use the algorithm, we can use validation to pick automatically the parameters for this fancy kind of regression where we have to set a parameter, all right? We're going to use that validation system where we have all the different choices, all the different setups we're trying, and we're going to run them through training on the same data, and then we're going to see what they do for validation on the same data. And data features are the same way, right? We talked about how what we might do is we might take a subset of the variables, right? We might, if we have elephant height and voting information, we don't want elephant height, we want to get rid of it, right? So we want to take a subset. And we might do transformations too. We might change weight and height into the body mass index. And that might give us a better time learning, maybe, okay? And again, these data features can be picked automatically through the validation process. So finally, what is that loss function that we talked about? Well, remember our definition for regression. We just want to find the slope and intercept of a line that minimizes the sum of squared errors, that we can draw through these cloud of dots and have the smallest total sum up of all of those vertical red error bars, okay? So that is the loss function for linear regression. For linear regression, we take the sum of the square of the errors, and that is what we're trying to squish down and make as small as possible to solve linear regression. All the other machine learning algorithms can be looked at in this same way, that there's some loss function that when this loss function is high, the algorithm is doing very poorly at its job. And when this loss function is low, it's doing a good job, okay? And we can use that same mechanics to solve all the machine learning, basically. Right? So now I think we've given you a taste. We've shown you that machine learning is just picking an appropriate model and what the model is, right? The model is the algorithm, the hyperparameters of the model, and the data features. And we just turn the mechanical crank and let the machine algorithm learn to pick the best parameters to let itself do the best job possible. All right, so that is all I had for you. I hope everybody had fun today. Let me know if you like having it broken up into lots of smaller lectures, if I should keep on going through this to bring a little bit more excitement in your life. And I will look forward to talking with you all again on Monday. Bye for now.